Hey everybody, let's give this op-amp problem a try. So this particular one has a potentiometer here. It's kind of like an adjustable resistor. You see how this end is just floating? It's not connecting anywhere. So you could have current going, for example, say this way, and then maybe it could go this way, we're not sure, but nothing would flow this way, right? Because it's not connected to anything. So this particular configuration is basically just an adjustable resistor, where from here to here, it's just this plus this in series. Okay, so just make note of the technique to work on this. Right? Nothing to be intimidated. It's just the same old KCL, right? So that if I call this node N, and if this is node P, and this is our output node. Okay, so let's just write KCL for node N. Okay, so let's go this way. So Vn minus 250 millivolts, 0.25 volts over 1.6K, 1600 ohms, right, is the current this way, plus the current this way, so plus Vn minus 0 over 6.4K, 6400 ohms, and then the current going this way, I'll just call that IN, and then the current going this way, which is Vn minus Vo over this resistance here, right, which is sigma times 50,000 sigma plus 12K equals 0, right? So there's KCL. And for an ideal op-amp, what happens, right? The current going this way and the current going this way are both 0, right? So this is 0. 0. Also, the voltage here is equal to the voltage here. The voltage here, Vn, equals the voltage here, Vp. Okay, but then, right, so ideal means Vn equals Vp, but look at this node. It's connected directly to the ground. Right, that's our reference. So Vp is 0 for this particular example, not always. So for this example, Vp is 0. And then for an ideal op-amp, Vp equals Vn, which means Vn is also 0, right? So this is 0, that's 0, that's 0. Okay, so that means we only have one unknown, where we want to solve for this in terms of a variable, this. Okay, so let's see, let's gather, let me just rewrite it. Okay, so minus, how about I multiply the entire equation by 1,000. Okay, so minus 0.25 over, I'll multiply this by 1,000, 1.6, plus 0 over whatever is 0. And then this would be minus V out over 50, and then sigma plus 12 equals 0. Okay, I'll move this to that side, somewhere like this. Like this, and then move this there. Okay, so so minus 0.25 over 1.6 times 50 sigma plus 12. There you go. So this is the output voltage as a function of sigma. All right, so what range can we have for sigma such that the op-amp does not saturate? The output voltage can't just be whatever we want, right? It can only be between 5 and -5. Right, so the output voltage has got to be in between these two, which means this, I'm just going to copy and paste, this has got to be between 5 and -5. There. Okay, so let's just finish this. So, okay, see the minus? If you multiply by a negative, then the inequality flips over, right? So I'm going to multiply by negative, or the reciprocal of negative 0.25 over 1.6. Okay, so that's going to be, that'll turn positive, so 5 times 1.6 over 0.25, and then the inequality flips around. And then this inequality flips around, and then negative 5 times 1.6 over 0.25. Okay, and then let me just subtract 12 minus 12 minus 12, and then just divide by 50, divided by 50, divided by 50, and there we go. Okay, so sigma is between these two values. Okay, let me just, okay, so already, without even punching in the calculator, this is going to be some kind of negative value, which we can't have sigma be negative, right? Because if you take a look at this, it's basically, you can turn a knob, right? So where this is just scaling from 0 to 1. It's like the percentage from here to here. So just physically, you can't turn the knob so the resistor becomes negative. So, right, just this becomes 0. Like it can't be less than 0, right? So just punch this in the calculator, and then this will be 0. So this 0, and then that's the answer. Okay, part B. Given sigma is 0.272, what is the current this current right here? Okay, let me just copy this picture again. Okay, so if we already know, we're going to use the value sigma is 0.272, right? Then you just plug that value in right there. Okay, so let me pause and actually get a number for that. Okay, so if I plug in the value, it just works out to be a nice even -4. Right, so this is if sigma is 0.272. Then the output voltage happens to be -4. Okay, so right here, the voltage is -4. And we want to know the current here. So just take a look at this node and just write KCL. Right, so KCL at this node, so the current going this way would be -4 minus the voltage here, which is the same as the voltage here, which is 0, divided by this. So that'll be 12K plus 50K times sigma, which is 0.272. Right, so that's the current going up this way. And then we need the current going this way. -4 minus voltage here, 0, over 10K. And then the current going this way, plus I/O. Okay, so then that's it, right? Just punch all this in the calculator and you have the value. Punch in the calculator. Okay, hope that was helpful. I'll see you in the next video.